Hello everybody, my name's Nick Howes. I work as the Research and Development Lead for the Space Systems team at a company called BMT based out of the UK. Probably the most famous thing we've done, because lots of people haven't heard of us, but we designed the Queen Elizabeth and Prince of Wales aircraft carriers, very famous in the naval and maritime domain sector and the defence sector. And recently in the last 2 years, we've kind of been working on our space side of the company. Anyway, so my talk today is on space debris. A little parody there on Julie Andrews with how do you solve a problem like debris-aahh. Please feel free to sing along if you so wish. So, what's the problem? Elon Musk, quite happily there giving an interview, doing something quite illegal at the time, or legal in some states anyway. And this is a key thing. There doesn't seem to be a perspective on the problem. That people don't seem to see that there's a problem with space debris, and this is clearly an issue. I'll just kind of highlight it during the course of the next 20 minutes or so in this talk. So, what is the issue? So the issue kind of began around about 1957 when humanity started putting things into space. First thing in space obviously being Sputnik, and closely followed then by a massive space race between the former Soviet Union and the United States, leading up to the Apollo space program and landing on the moon, and subsequently between the various defence and commercial industries that exist, we now have in excess of 3,000 active and inactive satellites in orbit. Now, this diagram that you can see here is kind of representative of part of the problem up to 2015. The problem is getting exponentially worse, however. We now have in excess of 136 million pieces of debris in orbit. And this is a result of the spacecraft being put up there since the late 50s, early 1960s, either disintegrating, colliding with other spacecraft, being impacted by micrometeorites, just generally exploding because of failed subsystems, batteries, etc., and leaving this absolutely enormous mess up in both low Earth orbit, medium Earth orbit, not so much in geostationary at the moment, but it's getting there. Low Earth orbit, key problem at the moment that we're all trying to solve. Now, it's not like humanity isn't aware of the impact that pollution can cause. David Attenborough and his incredibly wonderful Blue Planet series and various other programs that they've done have clearly identified the issue with plastics in the oceans. Now, plastic in the ocean is a massive problem, one that everybody's aware of, and as I said, David Attenborough highlighting this really brought it home to many people, many of the general public in particular. And the knock-on effect of that was that companies all around the world changed some of their policies. So due to the backlash caused by the use of plastics, and obviously right now plastics are very important with PPE, etc., but generally plastics, we can use other materials, and this has been proven. But the use of plastics had a massive impact on many companies. So large corporations all around the world changed from using plastic straws to paper and cardboard straws, for example, in drinks, changed some of their carton designs for drinks again and packaging. And it has had a really positive effect. However, this is still a massive problem. There are approximately half a dozen river systems in the Asia Pacific region which are causing most of the plastic pollution in the world, and the buildup of plastics around islands in the Pacific, Atlantic, etc. are quite significant. There are huge floating masses of this. Now, the thing about plastics in the ocean is that whilst it is a significant problem, it's a solvable problem. It's a definitely identifiable and solvable problem, because ocean currents tend to drift at a few knots, a few miles per hour. And hence you can have rescue vessels, salvage vessels, etc., or just modified, almost like modified fishing vessels in some respects, kind of fishing up the plastic, and in some cases being able to recycle it and reuse it, which is fantastic. But as I said, it is a solvable problem. We can stop dumping plastic into the ocean, we can stop dumping it into the river systems, and we can retrieve most of it, should we so wish, if we had the kind of financial will to do so. The issue with space debris is it's far more tricky. As I said, you've got upwards of 136 million pieces of debris. Now, these pieces of debris range from the size of a grain of sand and smaller up to the size of a bus. So the largest piece of orbiting debris, for want of a better term right now, is probably the ENVISAT satellite, which was the European Space Agency environmental satellite, and the irony of that doesn't escape many people, which failed in orbit. And this thing is the size of a school bus. Now, the issue with these objects is that they're not drifting around in the oceans at a few knots. They're travelling at 17,500 miles per hour on average. Some are travelling faster, depending on what orbit they're in, but the average velocity is orbital velocity, which is around about 5 miles per second, or around about 8 kilometers per second. Now, at those kind of velocities, the impact energy of something even the size of a grain of sand is absolutely catastrophic. Something the size of a pea could quite happily tear its way through most spacecraft. And if you were sitting in the cupola, for example, on the ISS, and something about the size of a pea were to strike that, unfortunately, it would be game over almost instantly. Now, lots of people have modelled this and demonstrated this. This is images from a debris satellite test. This was conducted in conjunction with the University of Florida, and they built basically a satellite full specification using all the standard systems, buses, batteries, power supply integration, went through the standard kind of AIT testing, integration and testing, and then it was put into a hypervelocity test chamber. And essentially they padded this chamber out with lots and lots of foam and fired something around about the size of a Coke can at it, at around about 7 kilometers per second. This is some of the footage from a very high-speed camera that was used to monitor the impact and subsequent collision. And essentially what you can see in the bottom right is that the satellite was vaporized. It was totally destroyed. Now, the last I heard was that it had taken them almost a year to pick the pieces out of the foam. They were upwards of 120,000 pieces of debris from that one satellite collision, ranging, as I said, in size from a grain of sand up to pieces of wire, small pieces of metal debris, etc. And that's just a small object, relatively small object, traveling at orbital velocities, hitting a satellite. So the collision of two larger satellites, you can imagine just what would happen. It's a significant amount of debris that would be caused. And these events are happening with alarmingly increasing frequency, these kind of collision or collision avoidance events. So thankfully, collisions themselves right now, there are a few cases, and I'll talk about those, but seem to be relatively infrequent. But with the exponential increase in satellites in orbit, and we'll point the finger, say, at the Starlink constellation, which has FCC licensing authorization for in excess of 30 to 40,000 satellites being placed in orbit, you can see what the problem could be.
Is off structure. Dr. Stone is off structure. Dr. Stone detached. Must detach.
Now, whether or not you love or hate the movie Gravity, it really did bring home the reality of the potential problem. Using human beings and astronauts really did hit home the significance of what could happen if there were to be catastrophic collisions in orbit. Now, what gravity highlights is something called the Kessler syndrome. So theorized around about 40, 50 years ago, this is where you get a domino kind of cascading effect of collision after collision after collision. So one object colliding with another creates a cloud of debris. That cloud of debris then shatters other objects, and you basically get this ongoing cascade until such point that the amount of debris that you're trying to fly through or launch through becomes, you just can't, it's unsustainable. Now, with Sandra Bullock and George Clooney, we obviously had all sorts of wondrous things like the use of fire extinguishers in space, which wouldn't really solve the problem of orbital dynamics, but most of the film was actually quite good. And highlighted some of the other problems that we've got, where we have nation actor states like China, the United States and India performing what's called ASAT tests, and I'll talk a bit more about that later. But essentially, what this has proved is that Hollywood can do kind of dramatic representations they did with Deep Impact after Shoemaker Leaving Iron and Armageddon. Again, you can discuss or look at the pros and cons and merits of those films as you will, but they did bring home to the public the necessity to look at the threat of potentially asteroids and comets striking the Earth, because a comet the size of Hale-Bopp, for example, at 35-kilometre wide, its nucleus would have been literally a global killer. It would have been a mass extinction event. And that really did bring home to the public in a grand scale what the issue was. And I'd say probably the same with gravity. If you've not seen it, please do see it, because it does highlight the issue. It's caused by a kind of Russian test. And there's a really good quote from George Clooney that most of North America just lost Facebook. And that's the problem. A lot of people don't see space debris as an issue. It's what's called the squirrel in the backyard scenario. Basically, if a squirrel dies in your back garden, you'll see it and you'll want to get rid of it. But if a squirrel dies in a forest a mile away, you won't see it and you don't really care because it's not impacting you. And that's the problem with space debris. People don't see it. It's up in the sky. It's kind of, you know, a rich man's playground, as it were. You know, or people are up there and astronauts, and it's all very gee whiz and Buck Rogers, etc. But it's not. The impact of such an event would be catastrophic on the Earth. I'll talk a bit more about that during the course of this. So, in terms of the number of objects, as I said, there are approximately 136 million pieces as of this year. So, first gave this talk last year, January 2019, 128 million. They now think there's over 136 million. Now, the scale of these objects means that some of them can be tracked and some of them can't be tracked. One of the most advanced tracking systems on Earth right now is called Space Fence. It's a defense system. That's capable of tracking objects in the kind of 5 to 10 centimeter kind of range. Anything smaller than that, you really can't see. And obviously you've got nation states that have got satellites up there that they don't want to be tracked specifically. And there's all sorts of efforts to kind of hide them and make them almost radar invisible, like stealth aircraft, and make them invisible to optical detection. All sorts of methods are being used to kind of for defense purposes to obfuscate this. So in terms of the objects that we do know about that are tracked, you can see some of the statistics there. And as you can see, it is a significant problem, and that's right now. That's not in the coming years when, as I say, you've got Starlink planning on launching anywhere between 30 and 40,000 satellites. And you've got other nation states going to do the same in response. Plus the UK government's just bought OneWeb, so that's several hundred satellites potentially there. You've got Amazon. And you've got a whole range of other companies all looking at these so-called mega, it's an inappropriate term, but mega constellations, these large constellations of satellites. And this is the scale of the problem. You know, and people say, well, it's not an accurate way to depict this because the space in between these objects is quite significant. And to some extent that's true, but the space in between these objects is decreasing all the time. The number of collision avoidance events per week currently happening is around about 13,000. The estimate is going up to around about 50,000 within the next 5 to 10 years per week. And that's if we get through the next 5 to 10 years. The thing is with this data as well is when you're looking at it, you think, well, you know, we've got a handle on where these objects are, and we don't, because we don't know where the smaller pieces are. And the error margins on a lot of these are quite significant. Most satellites, if they're not dynamically or actively tracked all the time, rely on what's called TLE data, so two-line element data. So somebody will calculate an orbit for a satellite, and then it'll maybe go around the Earth a few times, and then a reacquisition and a new orbit based upon its telemetry data, or you know, possibly a ground observation. We'll update the TLE data. But these things can be out by kilometers, literally by kilometers. Now, when you're traveling at 8 kilometers per second, that's a significant error. And there was a recent event over North America, potential collision event between the IRAS satellite and another defunct satellite. Which this is the thing, when they're defunct, you can't do anything about it. IRAS was an infrared observatory that was kind of shut down years ago. So no ability to use onboard propellant or computers or collision avoidance. You're literally just waiting for these things to either hit or miss. And thankfully they missed, but not by much. And again, if those two objects had collided, those two satellites had collided, you'd be looking at a significant collision event and significant increase in debris. Now, when I say about the collision of a small particle, this is a test that was done firing a small plastic pellet at a large aluminium block. And you can see the crater. The aluminium block in question here was around about a foot across and deep, and around about 8 to 10 centimeters deep. So if a plastic pellet can cause that level of damage at orbital velocity into a solid piece of aluminium, you only have to imagine what would happen to the relatively thin walls of most spacecraft. And yes, the ISS and various other spacecraft do have protective areas where the astronauts can literally go to hide and hunker down. And in some occasions, they've actually had to go into the Soyuz module for a potential de-docking and return to Earth. So yes, there are protective measures in place, but the entire spacecraft can't be shielded to that extent. And something the size, of a small plastic pellet doing that, you can imagine what something the size of a Coke can could potentially do to the ISS were it to hit it. And the ISS is a $200 billion space station that's the size of a football pitch, and it already has to move several times at least per year to perform collision avoidance events, or to miss collision with potentially threatening objects. But then we talked to statisticians and we talked to various people who've got a vested interest in this, and the people who are, nobody who works on satellites ever tends to complain about this because it's their livelihood, and you can appreciate that. But the reality is that you have to. And computer modelling says that we won't be hit by an asteroid, and computer modelling says we won't be hit by a comet. But Hale-Bopp in 1997 didn't miss the Earth by that much relative to its kind of orbit. It's a massive orbit, and we don't know what's out there and what's going to hit us. We really don't know. And people say, oh, statistics say this and computer models say this, and there isn't a crisis. We've got vastly improved artificial intelligence and station keeping and all these other mitigation measures in space, but you only need one collision event that you can't avoid from a piece of debris that you didn't know was up there. And when people say, well, what crisis? These people are worrying about the future, that it's rubbish. I kind of point them back to a talk given by a chap called Bill Gates at a TED conference some years ago, and he said the next great threat to this planet will be a global pandemic. Nobody took it seriously. A lot of scientists were warning about a global pandemic. Nobody took it seriously. People were saying what was going to happen. Nobody took it seriously. Everybody now takes it very seriously. The impact of COVID on our planet has been absolutely catastrophic. And the impact of a Kessler scale incident up in space will be equally catastrophic because we'll lose so much. Forget the fact that we'll lose, potentially lots of communication, and we may lose our television, and we may lose, some of our social networking capability, etc. I know we've got fiber optics that can replace many of that, and that's a good thing. We will lose global Earth monitoring. How do we get this climate change data? We get it mostly from satellites. Satellites observing things like the Amazon rainforest being torn to shreds, the fires in Siberia. All these things rely on Earth monitoring, EO monitoring. And if we lose all of that and the ability to launch, because the debris is so significant that we can't even launch things to get the debris down or to mitigate this problem, then we're stuck back in the late 1950s before we had anything. A lot of text here, but essentially this just goes into some of the NASA studies, National Academy of Science studies. These are significant bodies. These are significant people who are looking at this problem and saying we need to do something now. It's not a case of we need to do something in 5 or 10 years. It's we need to do something now. And the United Kingdom government and UK Space Agency have recently invested in 7 companies in the UK to look at the monitoring and tracking. And that's great. Looking at monitoring and tracking and identification and improving that is going to be a worthwhile exercise. But until we start thinking about how we're going to get rid of this and what we're going to do, it's just going to be continual build-up. Starlink are launching upwards of 60 to 100 satellites per month already. And if Musk gets Starship working, and at the rate of testing with SN5, SN6 being very successful, and SN8, We could be looking at that within a few years. And at that point, he has the capability to launch hundreds of satellites. India are already doing this now. PSLV is launching upwards of 100 small satellites at a shot. So we really need to take consideration and notice of this right now. And people say, well, these things don't happen. Well, it's not only collisions in space, it's objects deorbiting as well. And at the moment, the larger objects, some of the deorbits have been quite catastrophic even in our lifetimes. 1979, we saw the deorbiting of the Skylab satellite. Skylab was one of the first major space stations by the United States government, NASA, essentially looking at the sun and practicing, on-orbit activities for long durations. In some cases, it was several months. 3 crews populated it in the early 1970s, just after the end of the Apollo program, using Saturn V and Apollo hardware. Fantastically successful mission. It was still up there until about 1979. And one of the original intents of the space shuttle was to dock with Skylab and move it into a higher and safer orbit until they could kind of decide what they wanted to do with it. But it didn't work. And the space shuttle was delayed till 1981, as we all know. And in 1979, Skylab, several hundred tons of it, came crashing out of orbit and basically scattered its way all across Australia. And everyone in Australia remembers what Skylab was. And these are the kind of things that can happen. It's not going to be on the same scale as an impact of a comet or an asteroid, where you could be looking at potentially millions of people being wiped out. Something dropping out of the sky the size of even the ISS. And I'm not saying that's ever going to happen, because there's deorbit capability in that. As and when it does come to the end of its life, will probably end up at the bottom of the Tonga Trench in the Pacific. But these objects do fall out of the sky, and thankfully they fall in quite remote places, and over 75% of our planet is covered in ocean, so thankfully a lot of it does fall into the sea. But again, that's adding to the mess in the oceans. And some of these things have got radioactive generators on them, which again you don't really want polluting our oceans. So these problems are quite significant. And when I say pieces falling out of the sky, that's one piece of Skylab that was recovered in Australia. So these are significant pieces dropping on us. I mentioned earlier some of the larger pieces of debris. This is MVSat, and you can see in the image on the right hand side, somebody stood alongside it. Give you an idea of scale. As I said, it's around about the size of a school bus, a US yellow style school bus. And it's redundant and dead. And potentially that could collide with or be collided with by any number of objects. And you can imagine the amount of debris that could come from a significant collision with something that size. Now, people say, well, these events don't really happen very often. Well, they don't, but when they do, they are catastrophic. Now, this is a visualization using the AGI STK software between the Cosmos satellite and one of the Iridium satellites. So a lot of astronomers will know the Iridium satellites. We look up at them and you can predict the Iridium flares when the solar panels kind of incident angle to the sun is a good one, and we can see them kind of flare up, and it's a wonderful thing to predict. This collision happened in 2009, and this is some of the modelling that was done to show the significance of what happened with this and the number of particles that came out of it. So as you can see there, the two satellites, the Cosmos and Iridium, hit each other essentially at right angles. And this is the other thing, is that we have satellites now in solar, polar and sun synchronous orbits. We have them in equatorial orbits. We have a whole range of different orbits. Now, the debris cloud that came from this, the modelling showed that after the initial impact, this debris obviously went into its own orbit, independent orbit, and started to disperse. And these orbits are now complete no-go zones for any satellite, because there's so much debris in them that you literally couldn't risk putting things into these orbits. And this continues to this day. The collision was so significant and the debris kind of shot off in all angles that a lot of this debris is still up there 11 years later. It's enormous. And as I said earlier, you've also got deliberate, targeted anti-satellite weapons. So India, the most recent case, but China, Russia, and the United States have all conducted, what should we say, nefarious activities where they've tried to take things out of orbit. And India's last year was really reckless, and the Indian government and the Indian military were saying, well, no, it didn't really cause a problem. It was very low Earth orbit, and most of the debris will come out in a few weeks. That was proven to be completely false. The impact sent debris which is going to be up there for potentially 20, 30, 40, 50 years that nobody could predict. The impact collision was extremely high velocity and very significant. And this is an anti-satellite missile, so a missile fired from the ground to take out a satellite in orbit. And it was just saber rattling. It was an attempt to show their neighbours that they had very good capability in terms of anti-satellite weaponry, and that if push came to shove, they'd use it. And it's a real tragedy that, you know, any nation state in this day and age should need to do that. So the debris was far worse than predicted. I mean, they were saying low Earth orbit. Some of the debris exceeded 2,000 kilometre altitude. So 8 times higher, as it says there, than claimed by the Indian government. And this is the thing, as yet, nothing's been hit by it, but who knows? This is going to be up there for decades. And these tiny little fragments, you know, if they were to hit an astronaut on an EVA, that astronaut would be dead. If it were to hit a spacecraft with 6 people in it on a tourist flight in the next 10, 20 years, perhaps, they'd all be dead. And this is the scary thing, is that people aren't really taking this seriously, and we don't think anyone will take it seriously until somebody actually dies. And then people may take it seriously. At the moment, a satellite collision is a satellite collision, and they do happen. There's ones that aren't documented. There's military satellites that have literally just torn themselves apart. Images from the ground have shown them tearing themselves apart, and you don't know why. They've probably been hit by something small, but you can't say. And the issue with that is that there's no insurance liability either. So if you're in a car collision on the motorway, somebody's at fault. Could be you, could be the other driver. And the impact of that is that maybe the motorway is shut for a few hours while they clear the mess. If you're on a ship and you collide with another ship, even if it's in kind of a harbour mouth, you'll close the harbour for a few weeks or maybe a few months while you clear the mess. If this happens in orbit, there's no clearing the mess. It's going to just be up there and stop other people from launching it and other people from doing valuable science. And it's the valuable science that's the key thing. What's the solution? There's several companies actively looking at this, and they're doing a good job in many respects. Companies like Astroscale, Surrey Satellites. There's been all sorts of different kind of ideas and concepts and tests. But as you can see here, you've got thousands of tons of this stuff up there. And at the moment, a lot of the companies are focusing on one of 2 options. The first option is the kind of what we call one-to-one debris mitigation. So if you've got a smallish satellite that may be defunct, sending up another satellite to capture it, or to kind of harpoon it, or throw a net around it, as you can see here, and bring it down, is one of the options. Now, I'm not a big fan of the harpoon. I've got to be honest, because the laws of physics just kind of point to it being rather silly. If you get it wrong or you have a glancing blow, this was the harpoon, where basically the idea was that it's on a tether and it's designed to capture the satellite. Now, that's very nice when you've got a stick and a very static target and you've got a very controlled environment, but most satellites are tumbling uncontrollably. And if you get the harpoon shot wrong, then you could have an incident glancing blow. And at that point, you're just creating more debris, or you're sending the satellite into yet another uncontrolled orbit. So I've never been a big fan of this. The net idea is slightly better. If you can tie a net around it and bring it down using deorbit thrusters on maybe a small microsatellite. But again, you're putting up more satellites to get down just one satellite. And if they fail, or they go wrong, or they hit something, again, you're creating more and more mess. So this one-to-one approach, I've never really been a big fan of. Astroscale, this is another solution. They've got a better kind of proposal. Again, it's one-to-one, it's not a one-to-many, but essentially they've got electromagnetic tethers. So their solution is to look at the satellite that they're trying to deorbit, do a lot of risk assessment on it, look at the orbiting characteristics, much like the Rosetta spacecraft did when it arrived at Comet 67P. Went into orbit around it, modelled the characteristics, modelled the rotation rate of tumbling, looked at where the jets were coming from, did a lot of pre-analytical work, and then sent a lander down. And even then, as we saw with the Philae lander, it wasn't successful. It bounced all over and it didn't really succeed its full mission. So it's complex, it's really, really hard. Now, being able to model a tumbling satellite and then send out a magnetic tether that can latch onto it and then deorbit it, it's quite a neat idea. But again, it's just solving one satellite problem. And when we've got potentially 3,000 right now, 40,000 when Starlink becomes fully active. And Starlink already has a between 5 and 10% failure rate, depending on who you believe. There's a 5% failure rate that's been documented. So if you take 5% or 10% of 40,000, you're looking at 4,000 objects. 5%, you're looking at 2,000 dead or redundant objects in orbit. Now, if they're dead or redundant, you can't control them. You can't deorbit them. And currently, the United Nations kind of view on this is, well, you need to have a 25-year deorbit strategy and 25-year plan. In the last 25 years, the scale of debris up there has grown exponentially, and in the next 25 years, we can't even predict how much it's going to be. So as I said, the problem is getting exponentially worse. Now, this is a video of the Starlink launch, which many of us have seen, and I'm not kind of saying Elon Musk is evil. He's not. The man has done some utterly brilliant stuff with the Falcon 9, the Falcon Heavy. We've all seen those cores landing. The twin cores landing on the Falcon Heavy was almost akin to an Apollo moment for many of us. It was science fiction. It was like watching Thunderbird. It was amazing. But with Starlink, not only is he upsetting the astronomy community, and I'll talk a bit more about that in a minute, but the radio community, the radio spectrum side, is going to be a mess. And the amount of debris and objects up there is quite significant already. I said it's already causing havoc to astronomers. So when the astronomy community first started seeing images like this, where you've got a mass of Starlink satellites flying through images, and wide field astronomy, wide field sky surveys looking for potentially hazardous asteroids or comets, these are the ones that are going to be most significantly affected. Things like the Large Synoptic Sky Telescope, LSST, the EELT, and the Large Magellan Telescope. All of these large sky survey telescopes, or even the ones with narrower fields of view, are going to be affected by this. Now, when Musk first kind of started getting wind of the objections to the astronomy community, they did take some mitigation strategy, or they did make some mitigation attempts, building kind of sun visors and shields to effectively reduce the albedo and reduce the visual magnitude of the satellites. And they've been successful with this. So now you can't really see with the naked eye the Starlinks flying over, because naked eye visibility tends to go down to around about magnitude 6. And these shields that they've put in place drop them to anywhere between mag 7 and mag 8. So from a visual perspective, it's out of sight, out of mind. People don't see it anymore. But most astronomers have got telescopes and optical CCD systems that can hit magnitude 20 to 21. That's a logarithmic scale. So even my own personal telescopes, my own personal observatory in Wiltshire, I can hit magnitude 20 easily. So if a fleet of Starlinks flies through my images, when I'm trying to observe asteroid patterns or comets, it's catastrophic. And it becomes harder and harder to reduce this. And it's not only from an optical perspective, it's also from a radio telescope perspective. The FCC's license for Starlink and these other constellations, I'm not just blaming Musk, there's lots of constellations being planned, is eating up vast amounts of the radio spectrum. Now, if you've got radio array telescopes like the VLA or the Square Kilometre Array, which is going to be the most sensitive radio instrument in history. I mean, the SKA will be able to detect a radar, an airport radar, on a star system 30 light years away. The sensitivity of this thing is quite, pardon the pun, astronomical. It's amazing. So if you've got something like that and you're already having to filter out all of the noise and guff from the ground already, adding all that additional radio noise into low Earth orbit is going to have a massive impact. And the astronomy community is really quite upset about this and have voiced their concerns. But again, nobody seems to be listening. And people will only really start to listen when something really catastrophic happens. And that, sadly, is probably going to have to be the loss of human life. Now, as I said, I'm not just blaming Elon Musk. He's done some great stuff with Falcon 9, Falcon Heavy, and the plans for Starship and eventually going back to the moon and Mars. It can only be applauded. But him putting up massive constellations, and Jeff Bezos with Amazon putting up massive constellations, and the UK government with OneWeb potentially putting up massive constellations. How do you think our enemies, as it were, how do you think opposing nation states are going to respond? They're going to respond with their own constellations. So the Chinese and the Russians, as two notional adversaries when it comes to the defence sector anyway, scientifically we do seem to collaborate, which is a great thing. But from a defence perspective, obviously there are still ongoing issues. And they're going to put up hundreds or thousands of satellites. Make no mistake in it. So that 40,000 for Starlink, augmented by however many Amazon, OneWeb, etc. put up, you could be looking at anywhere between 100 to 120,000 new satellites in orbit within the next 10 to 20 years. And it's clearly unsustainable. We can't cope. There isn't enough, there really isn't enough room up there. All you need is a few collision events, and Kessler will probably happen. I'm not saying it will definitely happen, but it will probably happen. And unless we take action now, we haven't got a chance. So I kind of end it with this. Greed is good, because it's commercial interests that are driving this forward. It's not altruism. It's not, oh, we want to create the internet for everybody. We could do that with fibre optics. We could do that with ground-based systems. We don't need satellites to do this. We really don't. And as I said, there's lots of things to applaud about not only SpaceX, but all the other space companies. They're doing some remarkable work. But we really need to sit back and think about what we want to do with the space above our heads, because it's not that far up. And if we can't launch anything, then global Earth observation, climate change monitoring, all these things will go. Science as we know it, scientific exploration of the solar system as we know it, will go. So it's time to get our thinking caps on. And on that note, I'd like to say thank you very much. And if anyone has any questions, I'm more than happy to answer them.